So let's recall a few things which we did yesterday. Okay, I will not try to recall everything which we did before, but let's try to remember certain set of concepts. Okay, so what did we do? If you look at the main idea behind all the kernels which we made before was basically like greedy or looking at high degree. Okay, so this is what we had: high degree / greedy. Second, we try to do like we had an extremely powerful tool of sunflower lemma, right? And we saw its application in what all? De-heating set, D-set packing, and then we had some exactly red-blue dominating set in D-degenerate graph. Okay, and then we saw red-blue dominating set in Kij free graph, which was basically pigeonhole principle. If you notice, it was just pigeonhole principle, right? If k guy has to dominate all, 1 by k fraction has to be dominated by one guy. This is pigeonhole principle. Okay, if I did not pick him, then 1 by k fraction of this guy must be dominated by some other guy. Pigeonhole principle. So we can just say this was literally pigeonhole principle, and rest was just the maths to make it work, right? But the idea is that some point of time, I mean, so like if you just crystal out ideas, look, forget about examples, right? So this is what you should remember from here, not examples. Those are not important things. The important things are to remember these key features. Okay. And then we try to use matching. Okay. Okay. Then we try to use matching. Okay. And this is what called crown reduction, but never remember crown reduction. This is not the right way of looking at these things. This is like, I mean, then you are typecasted to think in a particular way, and that's never helpful. So what did we say? So let's just try to rebind ourselves in the language which we learned and which we try to expand. So what does matching theory tells us? It tells us that if you have a bipartite graph A and B, okay, so there exists a matching Pratibha, no need to write, anyway it's recorded. So just write down this and just be here, like, because it's slightly fast paced, you will miss the arguments, and this is my reason of why I'm recording it, so that like you write the just key points but don't write everything. I told them I said, because at this fast pace, like you will not be able to do both.
Okay, I'll try not to capture everything, but
just the key features, so that, and if you do not understand, just come back to my office, I will explain to you, or look at the that was my only reason for recording it, so that you can redo these things in your leisure. And here just listen, because I'm just telling you philosophy the way I view these things, okay, not the way it is given in the book. So if you'll miss this, you will not find it in the book. Okay, so this is like this PC course is completely from my own perspective, not from any book's perspective. Okay, so if I have an AB, so there is just a matching saturating A, if and only if, what was the criteria for all x subset of x, if you write n of x, cardinality of n of x is greater than or equal to x, right? So this is the classical theorem, and how do we try to apply? Okay, fine, either there exists a matching, so in all our applications, यहाँ पे बैठ जा, इससे ज़्यादा बेहतर दिखेगा, वहाँ पे नहीं तो तिरछा दिखेगा, right? So, and how do we try to apply this? Either this, so the cases where we apply, the way we apply cases, what happens is that we'll create A and we'll create B in a way. So basically, let's write down differently. Okay, B and A. If cardinality of A is going to be greater than or equal to cardinality of B, if this condition is going to, there cannot be a matching that saturates A, right? Just by the size constraint. Agreed? Do you agree? It just cannot happen. So this condition is also not going to be satisfied. So let's do contrapositive of this statement, right? So contrapositive of this statement is, okay. So what is the contrapositive of this statement? There will be some set, right, X here, right, whose neighborhood is smaller, right. So what is that? There exists X such that neighborhood of X, let's call it Y, is less than X. Do you agree to this? Okay. Now I am not going to work, so but there could be many such X's, many such X, right? I mean this condition could fail for many subsets of X. I am not interested in any, like, but I would rather say minimal X, minimal X. It means if I look at the subset of this, any subset of this, then the Hall's theorem is satisfied. If I take, what is the minimal subset? Minimal X, like what is the meaning of this? Is a minimal X which doesn't satisfy the Hall's condition. It means if I take any subset of this, it does satisfy the Hall's condition. What is the meaning of this? If you just let's rewind ourselves and try to think what is the meaning of minimal X. So let's zoom here. There is a X, there is a Y. For delete this vertex for now. Just now for every subset here, then look, first of all neighborhood of X is Y, then everybody's neighborhood is here only, right? But for this subset there is a subset of equal size. So if I forget this vertex, there is a matching that saturates Y, because I am applying Hall's condition on X minus say A, apply Hall's condition on bipartite graph between Y and X minus A. If X was a minimal set, it means here Hall's condition satisfied. What does it mean? There is a matching that will saturate X minus A and Y. So I get this, right? Now what you know that, oh, these guys were anyway looking at here. So now what is head, crown, body is exactly like, so your Y start to act like head, X starts to act like crown, and there is a matching that saturates Y because of the Hall's condition, and the rest is a rest, and by definition X only sees here. So why do I think like that? Because now if I think like this, I will never be able to do anything, right? From where do I create such a situation, right? So we go one step back and we try to think of this way, right? So take such a set and try to design a reduction rule, okay, rather than thinking of this way. So we should never think about crown reduction rule, right? We should always think about that, okay, I should try to create a bipartite graph between objects, try to get hold of Hall set, but not any Hall set, minimal Hall set. There could be many minimal Hall set, but you just find any one. That will guarantee you that there is a matching that saturates it, right? Otherwise, and you play game with this, right? So now for different application we played different game, different replacement rule, but at end of it, this is what was happening, right? So we were playing with a classical matching theory tool and we were trying to apply it differently, okay? Right. So if you go back, do we need to remember crown rule? No, we are just trying to create a bipartite graph to design a reduction rule, and for there we were trying to create a like up until now it should be standard. Whether it applies in your case or doesn't apply in case, that will be a problem dependent thing, right? But till here you should reach. You understand? It applies, then you will have the modification and something, okay? Okay. So having this perspective in mind, okay, so this is why I call matching based tool rather than saying crown rule, right? Because the moment I say crown rule, it will mean, oh, it's a partition of graph into head blah blah blah, and then you think from where do I am getting all this, okay? But now you know if someone says you crown rule, how he would have gotten here, right? So that's perfectly fine. So you know the translation. Now, okay. So based on this, we did vertex cover, right? Like very direct application of vertex cover. What else did we do yesterday? Right? But from this crown business, we were not able to do completely. So look at what we did. We did long cycle parameterized by vertex cover, right? So what was there? Here we created A, no, let's call them B, okay? A will always be for us bigger side from one. And what was A was equal to our independent set, but B was pair of vertices, right? So for situation, we will have a different object. And how did we, oh, let's give an edge between this vertex and this pair if it is in the common intersection of these things. Then we found a Hall set, right? And we said, hey, we can do some exchange argument. Like, it is not important how we do those exchange argument, because once you will see here, trust me, you can do your exchange argument yourself. You don't need me to explain to you, oh, this. Like, you really, if you sit down yourself, you will start seeing yourself. So important for us, at least in this lecture, will be, oh, we got here, then this lemma. So this word, and then we took matching and we introduced another concept, and this is a concept which you are not going to see in any book. So please take it. Okay, notion of redundancy. Okay. So I introduced the notion of redundant solution. Okay. So what is a redundant solution? Okay. So I gave you, but I never defined you. I actually don't know the definition. Okay. I myself don't know the definition. Okay. But let's try to quantify it. It should be good enough for you. Okay. And this has been very crucially used in all the newly designed kernels for caudal vertex solution, interval vertex solution, and blah 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 whatever. You will not see. I mean, if I will have time, I will show you the beauty of this. But because of this perspective, like we can rederive lots of old kernels in 2 lines. Okay. So what is a redundant solution? So let's we'll say, for example, S is a alpha redundant FVS, for example, feedback vertex set. So what is the meaning of this? Okay. This is not entirely true, but this is not how one should talk about it. Then it means for every cycle C intersection S is at least alpha. If it is one redundant solution, then it's just a feedback vertex set. Every cycle just intersects one. But if I say alpha redundant solution, every cycle must intersect with it twice, right? It's not always true that we will always have some alpha redundant solution for some alpha. Okay, but the objective of alpha redundant solution is try to capture some such things. Okay, and the best way to, how do we get these kind of solutions? So let's try to do this for feedback vertex set. So how did we did it for feedback vertex set? We said, okay, here is a way to do it, and if you don't do it cleverly, like the formal statement is slightly more difficult. Okay. So let's try to create 2 redundant solution, and then I will try to show you what it means to create 3 redundant solution. Okay. So let's try to make 2 redundant solution. So first you need to have some sort of approximation algorithm. Okay. This is one way of going about it. So suppose for feedback vertex set we have factor 2 approximation. We have factor 2 approximation. We know this, forget about it, like how, what, suppose it has a factor 2 approximation. So I have my graph G, I compute a solution of size 2k. Otherwise I can say no or whatever, doesn't matter. What is the property of this? It's one redundant solution because every cycle intersects with this at least once, right? When I say at least alpha, I'm not saying that it exactly, nobody knows, maybe there's a cycle completely contained inside this for all that I care, right? But at least I can guarantee that this set intersects with every cycle at least once, right? Fine. Now what I try to do for redundant solution, this way of looking at it, or the other way of looking at this is S is alpha redundant FBS if for all x subset of S mod x less than equal to alpha, S minus x is a FBS. I think this is a better definition. So even if I delete some alpha vertices from this, it still remains feedback vertex set. But for example here, if I delete one vertex, I don't know whether this will remain a feedback vertex set. Huh? Yes, let's put it, let's keep it alpha, it's fine. Because one redundant means if I delete, okay, you're right. Alpha minus 1, fine. Okay. So for example here, if I delete one vertex, I'm not sure that it will remain a feedback vertex set. But if I delete one vertex and it is not a feedback vertex set, it means what is not being captured? All those cycles for which this guy is the only one who, because anyway I'm deleting everything else, right? But only thing which I'm not deleting is some vertex A. It means only thing which is participating into cycle are all that passing through A. You understand what I'm saying? So how do I create this? So what happens is this. So now what I told you, okay, I said fine. Now let's make A undeletable. What I mean, A undeletable. How do I make A undeletable? I say let's put weight of A as 10 to the power 10 k, like some big number, okay?
Could you please explain the definition again? I am not feeling that comfortable with it.
So read it. So which part of the definition is not clear to you?
This S minus X.
It's a FVS. S is an alpha redundant feedback vertex set. If for all x subset of S, whose size is bounded by the something, S minus x is also a feedback vertex set. So there is some redundancy left here. For if I delete some alpha size, alpha minus 1 size subset, it is still remains a feedback vertex set. This is all that it says. So there is some, why it is called redundant solution? There is some redundancy has been embedded in this. Right? And corollary of this will be that every cycle will intersect this guy alpha times. It is like inbuilt here. Like whatever I wrote as a property, you can derive from here. No? Okay, good. Okay, so suppose, I mean this is like some, I shouldn't say some 10 to the power 10, say m, some big number m. What is my objective? What I want is that my feedback vertex set, and now I am going to run my weighted feedback vertex set approximation. Everybody has weight 1 except this vertex A. Now I run my approximation. What I am going to get? Either I am going to get 2k size solution or I am not going to get a 2k size solution, right? Either 2k size solution or some beta k, beta more than 2. If it's 2k size solution, then definitely not 2k, weight 2k solution, then definitely it cannot contain A, right? So it means I have found a feedback vertex set in my graph that doesn't contain A. So then I will write down, let's call this set SA, and I just write down. This set could be intersecting this set. I am not saying that they are disjoint or something, okay? Yes. But if beta is more than 2, what can you say? It means every solution of size at most k must be picking A, because if there was a solution which was disjoint from A, then I will get 2k size solution. It means there is none. It means if I am looking for a solution of size at most k, then this A is crucial for that solution of size at most k, then that is a reduction rule. I delete it and I am done. So either I will be able to apply some reduction rule, okay, or I will be able to get a set S. So if I apply a reduction rule, I am perfectly happy. Otherwise for every one I will get corresponding set, okay. Now if you take the union of all these guys here, I claim to you that this is 2 redundant solution. Why? You take out any 2 elements, right? I claim to you this is still a feedback vertex set. Sorry, not 2 redundant, it is 1 redundant feedback vertex set. Yeah, so it is 2 redundant, I think we should call it 1 redundant, alpha redundant means alpha, so that it is better. So in general, first one is 0 redundant, so that might be better definition, right. So now it is 1 redundant feedback vertex set. Why? Because if you delete any vertex, now why it is 1 redundant? If I delete any vertex, I have a set without him which is a feedback vertex set which is contained inside me, right. So this is it. Okay, now let us try to make it 2 redundant solution. Okay, so I will do the same thing, but now it is, the definition becomes slightly more tricky, and there is a reason why I am drawing like this. Okay, I will pick up A and I will pick up some B from here. Okay, I put A and B, some MK bit, B MK bit, and I still ask for a solution, right. Either I will get 2k size solution or I will get some beta k, beta more than 2. Then what happens? If it is 2k size solution, then definitely it cannot contain A and B. Then I have found for this A and B a solution which avoids both A and B. But if it is beta k, then what I know? Either A goes to a solution or B goes to a solution. So what I will create at this point of time, I will create a family F and I will keep AB. I cannot apply reduction rule because I do not know which one of them will go, but I just keep it. So at any point of time, we will have either, what is the meaning of this? So I will create this, so if I am able to get this set, I will keep this set, or I will get a pair from which, so at this stage you are looking for a feedback vertex set. So what is the property of this? Property is, look, either, what is the meaning of these guys? Every feedback vertex set contains these pairs. Every feedback vertex set is either a hitting set for this, it is a hitting set for this, right, or from here if you take out something, then it still remains a feedback vertex set. From this, if I delete now AB, then this is a feedback vertex set which avoided this. So this from here it is 2 redundant solution, but for some guys you have to have a hitting set pair. So this is how we generalize this. I just stopped it at 2 because up to 2 it's like a reduction rule. So you delete it and you are done. But as you go higher and higher up, you will have to keep a family of sets for which then you are looking for a solution which, and what happens when you do kernelization, it is like a de-hitting set. So I can store some k power d minus 1 elements, right, and say look, if any solution de-hitting set must kill all this and I will never delete those elements, right. I can mark those, look, this is a de-hitting set instance, right. So now I can prove to you, if you remember I said, hey, I can get a subfamily of this. What is the property of this? If there is a k size hitting set that hits all, if and only if it hits this subfamily, and that subfamily will have size what? K power d, right. So you collect all these elements, right, and you can encode either in an algorithm as a sets or by adding 2 cycles. I mean, based on the problem you will have to encode this somehow in your stage, but you can do these kind of things, okay, and these are very helpful things because these are like, basically what happens is that I have a problem where my objective is to kill big objects. So either I am able to get certain redundancy or I am plus some small de-hitting set instance. So it's like I have made a problem of de-hitting set plus big cycles, and big cycles looks like this. You will have to never worry about it because of it's like de-hitting set, and there are 1000 ways to capture this object, and so I can concentrate here, and then I will use this property that every cycle is hit 10 times, and then you start to play around with it. Okay. So this is a general philosophy. Okay. So this is how you define redundant solution. It is nothing about feedback vertex that I can define OCT, vertex cover, blah 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 blah. Okay. And using this we did a kernel study. What kernel did we do? If you notice, right, we gave using this one redundant solution, just one redundant, not even two redundant, we gave k to the power k square element kernel for 3 hitting set. And what was again what we did? We made a bipartite graph where in one side, but these code objects, right? One side we had universe, and if there was a family containing these two guys and this, then with this, and then we applied. But again we applied matching. So like now we have started to mix two tricks, right? So this is what we did. So we first applied redundancy and then did this. Okay. And what did we for feedback vertex set? To reduce the degree, again we applied redundancy, right? What we said? I wanted to reduce the degree of every vertex. So what we said? Okay, fine. Collect all this redundant solution, and for any vertex which is not here, this itself will act as a feedback vertex set. So there we needed for every V in VG, what we wanted, an set SV of size at most 2k, such that V is not part of SV and SV is a FVS, right? And how did we make this? We said fine, for all V not in VG, for all V in VG minus S, SV, S itself, because what is my goal? SV is, so S is a feedback vertex set of size at most 2k, okay? Initials. For any vertex outside, what is it? I have to give you a set SV of size 2k, so I took that set S, V is not, of course, V is outside, so of course V is not. SB is FVS, yes, of course S is FVS. So there's nothing. So only thing we needed to worry about is sets here, and for that we use redundancy to get these SVs, right? So this is how we created for every V in VG such a SV, okay? And then what did we do? Then we reduced the degree. How did we reduce the degree for feedback vertex set problem? We said fine, here are you V, here is my SV, here are my components, right? And every component he can have only one edge, because if you have two, then this cannot be a feedback vertex set which avoids V, right? And we said if then for every vertex here we marked some k plus 3 components, for everywhere we marked k plus 3 components, and the component which was unmarked we said, oh, delete this edge, and that was our reduction rule. That meant that we can bound the degree of these vertices by order k square, and hence we got a kernel of size order kq because of our regularity and bounded degree things. So this is where basically we stopped yesterday. Any question? I have, right? So there are 4 concepts we introduced. We introduced high degree rule, sunflower lemma, we played around with, right? Then we introduced matching, then we introduced redundant solution. So remember, these are the points to remember, nothing more to remember. Rest you will be able to play yours. And how do we make redundant solution? This is how we make redundant solution. If we have a factor approximation, and what are you looking for? You are looking for a solution which avoids this. And how can we do? Just give them extra weight so that you can never pick it. Like these are like little tricks, but these are the tricks to remember. Okay, any question before now I will change track.
When you're finding the two redundant solution, you're considering pairs from SA and within. So within S, don't you need to consider?
No, absolutely not. Because look at, why should I consider?
It is like how we're not considering vertices not in S for the first iterations. Is it similar to?
Look, pick up any pair of vertices, right? Pick up any pair of vertices. Pick up A, right? So either B is not here, then that itself is a solution. If B is here, then look at B, this would, I mean, what does it means? How to say this? So you want me to say that why are not picking 2 people from here and to make redundant? You could also do that. I'll send you the paper, read the proof, you will understand why it's not required. Otherwise you are going to, your redundant solution size will be like k power some f of d, where like this is a clever way of doing this, and this is a clever way of doing it, and you can prove why this suffices. I'll send you the paper, it's there in our interval vertex deletion kernel paper. There's a whole section involved devoted to this because we needed it. But for now, just grasp one redundant solution, and this is perfectly fine, right? We'll go to 2, 3, 4 when we require. First, let's eat up 1, and 2 you can make it for yourself. Okay. Any more questions? Okay. So now, what is my next thing on agenda? So I will change track now. Okay. Let's see what is there in my list. See, everybody has to work out. It doesn't happen.
So yesterday you said some expansion level you wanted to come.
Yeah, that's matching. We'll get there. Okay, so let's just do one for fun. One kernel for fun. Hopefully I remember. So okay, no more graphs. So this is called matrix rigidity problem. Okay. So input is a matrix M of say n cross M over some field F. Okay, let's not worry about whether it is real, Q, finite field. Let's not worry about like some FP or something. Okay, but it's some field. Okay, and an integer K. Integers K and R. Parameter is say KR both. Question: can we edit K entries of M? By edit means can I change this by some other entries of R of M such that can be of M and obtain M prime such that rank of M prime is at most R. Is the question clear? So I have a matrix M, say n cross M, n rows, M columns, right? Okay, and I want to change some K entries, right? Change some K entries, okay, such that now when I look at like I want to change this, modify these entries, such that if I can modify these entries like, right, then the rank of this guy will become at most R. It could have very huge rank. Can I change some K entries over the given field such that the rank of this matrix becomes at most R? Okay, is the question clear? And now we are trying to give you some reduction rules which will reduce the dimension of M to some function of R and K. We say, hey, if you want to change this matrix and change the rank, then it is better that you change the rank of this smaller matrix, where the number of entries will be some function of K, some poly function of K and R. Question clear? Okay, so let us try to achieve this. Okay, so here is my procedure to do this. Here is my matrix N. Okay, so first let me tell you how to reduce rows, and then you can reduce the columns accordingly. Okay, I find if the matrix has rank already R, do we need to do anything? No need. I mean, hey, we are done. So fine, I find and you know that the rank of a matrix is invariant under permutation of rows or columns. Do you agree? So I just find rank, like I rank row rank, I find row rank any bit that is equal to column rank. So I get some if there are too many of them, okay, if there are too many of them, say strictly more than R, it could be, I don't know how much it is, I bundle them. I said, okay, you are my first R plus 1 and I move this. So this is R plus 1 linearly independent columns because they are forming a basis, right. So if you have a basis, then any subset of those columns are also linearly independent side. So there could have been many more, but what did I do? I just kept R plus 1 and I moved up. Okay, now I look at, let's draw bigger, okay. Okay. From the remaining guy, so I left this R plus 1 if there is strictly less than R, then there was nothing to show. From the remaining guys, I again find the basis of this sub people, excluding this R plus 1 rows, right. Either I will get at most R or R plus 1 or more. If whatever I get, I find another set of bases of size R or R plus 1, whatever it is, but I kept R plus 1. I keep repeating this process K plus 1 times. If this itself covers all the rows, I am done. But what is the property of these guys? Notice, first of all, if this is R plus 1, right, I keep doing this. How many times I will do? K plus 1 times, okay. K plus 1 times. Imagine yourself, I do this K plus 1 times and every time I get R plus 1, R plus 1, R plus 1, R plus 1, what happens? Huh? Can I say no? Because look, whatever it is, you will have to make one modification here. If you don't do, then there will always be a sub matrix of dimension R plus 1 times R plus 1, whose rank is R plus 1. Because if you have, so I mean this is linearly independent, right. So if you don't touch, they will still linearly independent over the field, no. So you have to make a change here, you have to make a change here, you have to make a change in every guy. So the last K plus 1 guys, or somewhere you will be actually storing at most R rows. Otherwise, if you went till K plus 1 with R plus 1, 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 you can say no. Agreed? Fine. Excellent. So this is R. Agreed? Okay. Now I am going to say, or maybe it is at most R long back, like somewhere already. But how many rows did you store? At most k plus 1 times r plus 1 at most. I am telling us let us throw all these rows. Okay, I have not done the column reduction, I am only done the row reduction. But what is my reduction rule? My reduction rule is throw me. Okay, so this is my reduction rule. Now let us prove it is correct. Okay, let us call this m row up until this. So what is our matrix? M k r if and only if m row k r, right? Forward direction is trivial. If I can make k modifications in this whole matrix such that the rank becomes at most r, then I just do corresponding modifications here, that also will be there. What is hard part is to show the reverse direction. Why if you only do modification to these little guys, it is sufficient here. Okay, do you see the proof? Okay, so okay, let m row mod be solution to to reduced instance. What I am going to do for this, I am going to put on the top m row mod the modified thing, and here I am going to put below throw me. This is my modification for the original graph. Okay, so I look at the first set of this, I have a modified solution, I replace this and I keep below, and I am telling you if this guy had a rank at most r, this whole matrix has a rank at most r. Why? I'll give you a few minutes, think, it's not hard. Please use pigeonhole principle.
Only part is dependent on the last R independent less than equal to R independent.
But maybe I have made a modification there. Okay. How many blocks do you have? How many edits are you allowed to do?
Okay. So there will exist a block.
So there exists a block which I did not edit. Fine. So let's see this block. Okay. What is its rank? It cannot, look, I didn't make it. So it's already at most R. And this, it means this was the basis. What did I do? Find the basis of the remaining guys. If it is more than R plus 1, then just keep R plus 1. Otherwise you kept the basis. So this was the basis, I did not choose. It means every one of them is linearly independent of them. And that's it. Pigeonhole principle. Because if you do the basis, every column can be taken linearly, like linearly dependent on these set of rows. And that was the basis of size at most R. So you are done. Okay. So throw me is fine. Okay. So you do throw me. So you do this. Now you do the same thing for column. You column, 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 and then you will get set of columns which will say throw me, and that's it, right? So you will finally get a matrix of dimension at most k plus 1 times r plus 1 times k plus 1 times r plus 1. Okay, so this is just a dimension reduction. And it has nothing to do with field, right? I can work over any field and do this dimension reduction, right? So what was an idea? So let's go back again. We made blocks by pigeonhole principle. And what is the greedy approach? For the remaining, find a basis. If it has size more than r plus 1, then only keep r plus 1. If it is less than or equal to r plus 1, keep all, like keep the basis. Okay. Now, if this is a yes instance, by pigeonhole principle, some block was not touched. Keep that, take that block. It means there you would have kept less than or equal to r row. It means beyond it means everything else can be written as linearly dependent on these set of columns. So you are done.
So Thobi was not there in this.
What?
Evro K earlier.
Yeah, it was not there. Yes.
So those.
Throw me is not in the k plus 1 blocks, no? But that guy has a rank at most r. It means that particular block had rank at most r even before. It means if I look at this matrix from that particular block and everything below, it had rank at most r anyway, right? Which means that every column here, every row can be written as a linear combination of these guys, and that is exactly what we used. So throw me can be thrown. Do you get my point? Okay. And now I can do similarly for the columns and reduce the columns. So now I will find column rank like this. And then do this. Okay. But this is not a kernel. Why it's not a kernel? It will depend on what field these objects are. But what we have been able to reduce is the dimension of the matrix. If you have been working with finite field, then each entry has small number of bits. So it is a real kernel. But if I am talking about reals or rational, I don't know how much bits each of these numbers are. So I cannot say it's a kernel. It's just a dimension reduction technique. Question? Okay. Now let's do matching on steroid. So what should I rub? Should I rub the problem or do you want some time? Now I want to do matching on steroids. Okay. 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 If I give you a bipartite graph, let's ask ourselves the following question, and that will answer lots of questions. Okay. If I give you A and B, okay, it's a bipartite graph. Okay, bipartite graph, and I want two edge disjoint matchings that saturates A. Do you understand my goal? I want two edge disjoint matching that saturates A. So how will that matching look like? So suppose, no, this is not what I want. This is not what I want, sorry. Okay. Let me define a star matching, okay. So what I am going to call Q star matching, okay, Q star matching. I am defining a new notion of Q star matching. A set of edges is called Q star matching if endpoints of these edges in B are disjoint. Okay, so in B they are all disjoint. However, in A, for every vertex, for A in A, there are Q edges incident to it. Okay, so how will this object look like? So it is like this, it's like 2 star matching, like this. So in B they are disjoint, but in A for every vertex there are 2. So if 3 star matching will look like how? They are still disjoint in B, but in A they are incident like this, like this, like this, like this, like this. You get my point? So this is what I mean by Q star matching. So it's basically a set of edges whose endpoints are disjoint in B, but when I look from the A's perspective, there are Q edges which are incident to every vertex. Okay? So 1 star matching is a normal matching. I want a condition like Hall's condition for this. Can you give me? You get my question? I want to say there exists a Q star matching from A to B, like there exists a Q star matching saturating A if and only if what? Get my question? I want to prove some sort of, so what I would like to prove? I would like to prove the following statement, okay? Okay, so here's the theorem or lemma I would like to prove, okay? There exists a Q star matching saturating A if and only if what? At least that is required, right? I mean, otherwise it's not going to happen, okay? I mean, so one direction is trivial, but forward direction is not trivial, right? That if exists a Q star matching saturating A if and only if for all X subset of X, neighborhood of X is greater than or equal to Q times X. How will we prove this? So doesn't it look like a matching on steroids? It's a matching, right? If I told you expansion lemma and blah, I mean, it's a completely useless thing. This is not how, at least I thought about it 10 years back. So this is not how you should think about it in 10 years now. These are some of the terminology which I developed. So this is not how I developed it. How will we prove this? Which direction is obvious? Forward direction is obvious. Now we have to show that this is sufficient. My only hint is, let's give a reduction to Hall's theorem. Yes. Okay, so what we'll do, we'll keep B. So all of you believe that forward direction is easy. Do you agree? Right? Like this is like nothing, right? Okay. So now for A, I'm going to make A tilde. Okay, what I'm going to make A tilde. For every vertex, make Q copies. For every vertex, say AI, let's make it AI1, AI2, AIQ, and give them same adjacency as AI. That's it. So this is my construction. Okay. If I can show to you there exists a matching that saturates A tilde, am I done? If I show to you there exists a matching that saturates A tilde, am I done? So for each vertex AI, I made Q copies, and suppose AI was adjacent to say X, Y, Z, W. Suppose, then I make all these guys adjacent to exactly X, Y, Z, W, so that I can, whenever I get these edges, I can identify them because they all are adjacent to A. So that is the whole idea. Okay. Now all I need to show that this satisfies Hall's condition and we will be done. Right? Because now what I am looking for, it has a, now I have told there exists a Q star matching saturating A if and only if this is same as saying there exists a matching saturating A tilde if and only if something satisfied. Right? That's all that I have to show. Now I just do a normal thing. I don't have to, like if I show there exists a matching saturating A tilde, then I would have shown what? Reverse direction. I have this property and I have to show there exists a matching that saturates this, right? And to show there exists a matching that saturates this, all I need to show is Hall's condition, right? So let's try to show some Hall's condition. Given this condition, we have to show this satisfies Hall's condition. Isn't that obvious? Right? Look at these guys, set of guys, right? Look at this set of guys. What I have to show? That suppose here I have some x, here I have to show that n of x is greater or equal to x. This is my goal, right? This is my goal. So you pick up some set x, this is in A tilde, right? So without loss of generality, if I have some copy here, I can keep all those copies because they have the same adjacency anyway. Look, I have to show little people, like neighborhood is more than some little people. I said actually neighborhood is more than even more people, right? Very good. So in X, because their neighborhood is same, right? But what is the property of, if I just take singletons here, what is the property of these guys? What was the property? Look at this. So look at the corresponding guys here. What do you know about them? You know about them. Let's call them X tilde because we were talking in X tilde. Look at the image of X tilde in A. Image of X tilde in A. Right? Let's call it X. So what you know? N of x is equal to n of x tilde because, and what is this? This is greater than equal to what? Q times x. But what is what? And this is equal to x tilde because for every x we have q copies. So haven't we showed this? Right? So they are just matching that such. So if I have this condition satisfied, then I have such a matching. Agreed? Is it okay? Good. So how are we applying Hall's theorem? We had two sets, we wanted to reduce one set, that set was bigger, so we were looking for matching, so blah 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 will happen. Okay. So we'll do the same, and that is exactly what expansion lemmas are. Okay. So now is the proof clear? Okay. I'm not going to talk about expansion lemma. I'm just going to tell you how we are going to use it, exactly like matching theory. So why do we need to know 30,000 theorems in life? Okay. Is the proof clear? I mean, even if it is not clear, if you think through, I mean, it should be clear. Okay, so the way we will use it, and I will show you how to use it with a couple of simple application like feedback vertex set and blah, I'll show you. So the way we use it, we will have B as always. Okay, here is A. Here is A. Okay. So we will have some set A and there will be have some set B. So either we will say either Q times A, fine, then nothing to reduce, or Q times A. Okay. So then what will happen? Either you will be able to find Q star matching and then you will do something about it. Then what will this imply? There is a subset X, there is a subset X whose neighborhood is Y, right, whose neighborhood is Y, and what is the property? Neighborhood of Y does not see anywhere, and if I take minimal, then what is the property? If I take minimal such X, it means you could look more than Q times A, right? For each of them there will be a matching, Q matching that saturates X, and there will be some additional guy sitting here. You get my point? Look, this, what is the property? Neighborhood of Y, look, Y is less than Q times X, and it's minimal such object. It means for everybody else I have a Q guy saturating. Is that correct? Or I am saying something wrong? Or I am saying ulta?
Some element does not have Q matching.
Q star doesn't exist, so cardinal
The
to
W
NX
belongs
is
to
strictly less than.
It won't have QHS.
Wait. How are we using it before? For matching?
X is minimal. That means if I remove one element from X, I will get a matching saturating X. Now if I remove one element from X, I'll get Q star from X.
Is this how we use it? But that's one way of using it. Okay, we'll see an application and then we'll try to get it out. Then we will see how to get it out from where. Okay, but principle should be same. Okay, maybe I have a problem with making it abstract. Okay, what does it says? Okay, so this is what it says. Okay, so this is a theorem which we proved. Here is a lemma. What it says, let A comma B be a bipartite graph. Okay, let A comma B be a bipartite graph. Okay, such that first Q times A. Okay, second, there are no isolated vertices in B. That's okay. We also needed this for matching. Okay, so here is A, here is B, cardinality of B is too large. This implies there exist there exists X subset of A non-empty and Y subset of B such that, okay, such that X has Q star saturating X with endpoints in Y, okay, and Y has no neighbor outside X, okay. So I will find an X and basically Y will be neighborhood of X, and here we'll have everybody this, okay. This is what it says. Okay, and you can find such a set in polytime. Okay, so this is another way of using it, where what we are saying that if look at this condition, all it says that for cardinality of B QA holds, right, but to guarantee that there exists a Q star matching saturating A, I need to hold this for every subset. But he says if it may not hold for some subset, but still if you have a cardinality guarantee, then I can find two small subset where this expansion happens. This is what it means. And how do you prove this? Okay, let's try to prove this. It should be some obvious. It should be some obvious way of proving it. Okay. Here is A, here is B. Okay, I got it. So if there is the matching that saturates A and B, if there is a Q star matching that saturates A and B, there is nothing to prove because I can take X equal to N of B. So this does not hold. What is the meaning of this? There is some subset X here and N of X here with the property. What is the property? Huh? X, N of X is strictly less than Q times X. Do you agree to this? Okay. So we want to apply induction on N, which is mod A plus mod B. Okay. So base case is like fine. Now what I would like to do, look, X is a non-empty subset, Y is a non-empty subset. Now let's look at A minus X, B minus N of X. Okay. If I want to apply induction, I have to show some property, right? So what is the first property? If I want to apply, cardinality of this should be Q times this. But we removed some set here, but less neighbors than them. So this property is definitely satisfied. I removed P guys, but then I removed strictly less than P times Q. So the number of the the size of B minus NX is still Q times A minus X. So this condition is satisfied. Okay. Second, there are no isolated vertex in B. Why? Look at these guys, right? Look at the guys which have been removed. I removed all his neighbors, right? So if there was no isolated vertex before, there cannot be any isolated vertex now. So I can apply induction and I can find this cell. Okay, fine. Right? So this is nothing but a simple induction. Okay, but yeah, this is a simple induction. You can also prove all theorem like this actually. Okay, so now we have learned. So this is a form people use it, but I also like to use directly this in lots of application, which will be useful. Either I find an expanding set, use that to make some things, or you find this cut set with smaller objects and try to remove some irrelevant vertex. So please remember both perspective, expansion perspective and the cut perspective. Which application will need what? I mean, you have to try both. Okay. So it's 25. So what should I do? Let me give you not feedback vertex set. Let me give you a very simple example of this, like extremely simple example of this, and then we'll break it. We'll make it a break. Okay. So is the proof clear? Like this is just a matching theory, okay? And this is what they call expansion lemma. Huh? Yeah, I'm not giving it a name. This is exactly my point. They are same. Okay, this Q star and all this is my terminology which I made on the fly. In the book you will find something. Okay. Because I have like, I hope they use the same thing. No, they call Q expansion. But it's okay. So let's generalize vertex cover. Okay. Since you people are since it is India, let me use the full name. Otherwise, people might complain against me. Okay. L component order connectivity. Okay. You understand what I said? No, you need to have a. Okay, not going. Your kids, and I'm not Daniel. You will read book, he will understand the joke. Okay. So what is component order connectivity? I want to delete k vertices such that every component has size at most L. Okay. What is this? Does there exist k vertices whose deletion leaves components, when I mean components, connected components of size at most L? Okay. So if I put L equal to 1, what is this? Huh? What is L equal to 1? Yeah. Huh? So what is L equal to? What problem is this? हाँ भैया कस के तो बोलो. Right? Because every connected component has size at most 1. Yeah. अब 0 तो ना होगा. So can you give me an approximation algorithm for this problem?
Find a 4 size, like do a 3D type of search.
4, where is 4?
Oh,
It's
sorry, n plus 1.
okay.
N plus 1 size connected to some graph.
And delete all the vertices, right? Look, if I find a L plus 1 size connected set, at least one of these vertex must be deleted, right? The way you find an edge. Okay. So here is my stupid simple. Delete all connected set of size L plus 1. So you delete, add, delete. I mean, you understand what I am saying? That like delete all connected. This is not correct. Delete a connected set of size L plus 1 and keep repeating in the remaining graph. Okay. You understand what I mean? Okay. If I start to go formal, we will unnecessarily. We all have understood what it means, right?
We can also do this now. We have this for vertex cover, we find matching and like take all the inputs. Here we can do this L star thing and take all the inputs.
Which is same as this, no? How it is different? I like there you find an edge, here I found an obstruction, deleted it, or find another obstruction, deleted. That's it. So what is the factor of approximation here? Let's use margin to get a kernel, like Fermat's. Okay. So what is an approximation factor of this algorithm? Right? I delete L plus 1 size, right? At least one will go. So it is a factor L plus 1 approximation, right? So if I put L equal to 1, this is a factor 2 approximation for vertex cover. L plus 1 approximation algorithm. So suppose I get a set S, right? Because if its size is more than k, like if strictly more than that, we can say no, right? Because if I have a factor L plus 1 and I get this by greedy approximation, strictly go, then we can say you need more than k vertices. So we have S. And what is here left? Right? Do you agree? Atmos L. Now I want to apply one of these lemma to reduce objects. I have written everything on the board. There is nothing. I mean, there is A, there is a B, everybody is sitting there. Who is big? Who could be big? These guys could be big, okay? So big guys are big, okay? So now which Q to choose you have to understand first. When we were doing vertex cover, Q was 1 because 1 itself represented an obstruction. But here suppose I make one guy and make him adjacent to this component, like whatever that meaning. I cannot say that this plus this forms an obstruction because this could be size 1 for all that I know. You get my point? Right? Or like the size of this connected component could range from 1 to L, but I don't know what that. But if I pick L component adjacent to him, I am sure that this together forms an obstruction because at least each of them will be contributing 1 to the connected component, and since this guy is connected to all this and we will formalize that, it forms some connected set of size maybe not L but strictly more than L for sure. You get my point? And that forces us that, oh, I don't need 1 but I need L expands. Okay, so this is a way. So now, okay, so first of all we need a model graph. So what will we do? So for each connected component, let me add a vertex in my graph, okay, which represents this connected component. So for every connected component, I add a vertex, add a vertex, add a vertex, add a vertex, and if this vertex sees any vertex in this connected component, then I add an edge. Is a construction clear, right? If this connected component is neighbor to this vertex, then I add an edge. So now it truly represents that connected set in my original graph if I look at some stars, right? Because I did that edge because this guy was looking into him. So now this red guy forms my B. Now I will say, is cardinality of B more than Q times, sorry, L times S? If it is, then what will I find? Let's see what will we find. Then we will find a set X here with Y here, and everybody of them can be assigned to L components. And what is the property of these connected components? They do not see any guy outside, right? So my claim is it's best to pick x into your solution. There always exists an optimum solution containing all of x, just like vertex cover. Because look at any optimum solution, it will pick one of the guys. If you do not pick this, you have to pick something from here. You have to pick something from here. You have to pick something from here. Then it's better that you pick these guys because they can do more job than picking these guys. This is exactly like vertex cover. So you delete all this, done, reduction tool. Okay? Okay. So what is the size of this kernel? Here we have L plus 1k and we stopped here, then what is the size of B? Plus L times L plus 1 k, is that all? Which is at most L. So basically this kernel is of size order L cube k. But now let's notice few things before we leave. Now look at all those components, right? I don't know what their sizes are. If suppose you told me that every component has size at least L over 2. I mean, I don't know, but suppose you were able to tell me every component has size at least L over 2. Then I am saying let's apply 2 expansion. Why L expansion? Because when I do this, L by 2 is L plus 1, I need to hit this. The reason why I went L, because then only I can guarantee that I have gone beyond L plus 1, right? So here is an exercise for you. This is an exercise. Order L square log L times k kernel, you get it from here, okay? So I can reduce at least 1 L to log L. But this also demands, now if you notice that maybe we need some weighted version of expansion lemma where weight will correspond to the size of this component, right? And that led us to define the notion of weighted expansion lemma, and if you apply that, which I am not going to give you a proof, see the book, then you can save off this log k, okay? And if we really work very, very hard, we can also get rid of the square, but that requires way more hard work. But with direct application of expansion lemma, like weighted expansion lemma, you can get rid of this. So you have to play, then you have to play games like fair division and this and that, I mean some LP and all, so this requires slightly maturity, it's there in the kernel book, but this is where it came, right? But to get to this is really a good exercise. I mean, and my point is, you know this, it's not something which I am, as I told you, right, if every component had size L by 2, what would I have applied? Right, and if every component would have size 1, then do I need to do anything? Okay, anyway, I leave that to your imagination, okay, so we'll talk at 2.